Welcome to the lecture on the integration formulas and the net change theorem. So we're going to work on simplifying the notation for antiderivatives. The fundamental theorem of calculus part 1 says that if f of x is continuous, then an antiderivative of f of x is given by this integral. FTC2 says that if capital F of x is an antiderivative of f of x, then we can evaluate this integral by evaluating the antiderivative at b and subtracting the antiderivative evaluated at a. So this is what we worked on in the prior section. So traditionally, the indefinite integral, which means there are going to be no limits of integration at the lower and upper ends of the integral symbol, is used to represent the antiderivative of f of x. And we will switch to calling the antiderivative just the indefinite integral, or more simply, the integral. So we would say this is an indefinite integral, so we would say the integral of f of x dx is capital F of x. So instead of calling it the antiderivative, we could simply call it the integral. The meaning here is that the derivative of the antiderivative is the function itself. So let's talk about notation a little more. A definite integral is a number. So this would be a definite integral. Between two numbers, you integrate the function and you arrive at a value. An indefinite integral is a function. So we'd have no limits of integration shown. So we're actually finding the antiderivative of x squared, and this is the antiderivative. So an indefinite integral is what we called in the past a antiderivative. So now we can just call that an integral for short. An integral is an antiderivative. So a table of formulas is useful for quickly finding the integral of a function. And we're going to look at a table of the common ones that we use. The formulas can always be verified by differentiating the right side to obtain the integrand. Just like if you looked at this one here, if I took the derivative of this side, I would get back to x squared. Here's another example. The integral of secant squared x dx is tan x plus c, because the derivative of the right side, that's this, takes you back to secant squared. So here's a table of some indefinite integrals, or integrals for short. So we use some of these all the time. So let's look at the first one, for instance. Here we just have a constant times a function. So we know that we can integrate the function and multiply that by c. So then here's one, k times dx. So the integral of k times dx is multiply k by x, and you have your antiderivative, or your integral. If you differentiate k times x, you get k. So you can check it by differentiating the right side. Here's the power rule. If you differentiate this, you get back to this. Here's e to the x. If you differentiate e to the x, you get back to this. Here's negative cosine. If you differentiate negative cosine, you get sine. So the integral of sine is negative cosine, and so forth. So here's tangent. Here's secant. These are ones that we've studied in the past. Here's inverse tangent. The derivative of the inverse tangent is 1 over x squared plus 1. So the integral of 1 over x squared plus 1 is the inverse tangent. We haven't worked with hyperbolic cosines and sines in Calculus 1. Here's one we know, etc. So you can look all the way through here and you can see you're going to recognize all of these except for the hyperbolic cosine and sine, which we haven't studied. So the usefulness of a table is that you can do these problems more quickly. So let's review what we know about integrating an even function. So an even function would be symmetric about the y-axis. So that means f of x is equal to f of negative x. So for instance, f of 2 would be equal to f of negative 2. So if you integrate symmetrically, that's on the same amount on either side of the y-axis, you're going to find out that you can just double the integral from 0 to x, because this side here, this blue shaded region, will be the same area as this blue shaded region. So we end up being able to simplify this by just doubling the area on one side. Right? We can see that would be true here too. This area to the left of the y-axis is equivalent to this area to the right of the y-axis. So if I integrated between negative 1 and 1, if this was negative 1 and 1, I would be able to double the integral between 0 and 1. If you're integrating an odd function, we know odd functions are symmetric about the origin. So that means that f of x, so if we're talking about pi, for instance, f of pi would be the opposite of f of negative pi. Right? And that's true for any x value. So the way that we can simplify integrating an odd function is to say that this area cancels out this area. This would be a positive area. This would be a negative area. So if you integrated symmetrically about the origin, the same amount to the left and to the right, you're going to get a net sum of 0. So this is just a review of integrating even and odd functions, something that we've already discussed and done some problems on earlier. So now let's talk about the net change theorem. The theorem says that the integral of the rate of change is the net change. So the integral between a and b of a rate of change function with respect to x is the function f evaluated at b minus the function f evaluated at a. So something we've worked with a lot is the velocity as a rate of change function. So if I plot the velocity versus time and I integrate that function between a and b, I'm going to get the accumulated area under the curve. Well, velocity times time gives you displacement. So like feet per second times seconds gives you feet, right? So this is going to be your feet, and this will as well. So if some of your graph lies below the x-axis, though, we know that this is a negative area, and then the part above the x-axis would be a positive area. So you could end up with a net displacement, either a positive number or a negative number, and that would be with respect to your starting point, like 0, for instance. So that's for velocity. So like we're pointing out, this would be v of t, and this would be s of b minus s of a. So the net change theorem principle can be applied to rates of change in the sciences, business, and engineering, where we many times are studying the rate of change of a quantity with respect to some independent variable, which may be time or something else. So here's a few examples. The change in velocity with respect to, this is volume actually, the change in volume with respect to time is the rate at which water, for example, flows into a tank. C prime of x is the marginal cost of producing an additional unit. So this is a business application. And then we just talked about velocity up here. So we're going to work some of these kinds of rate of change problems in this section. So our first example here is a practice problem on how we integrate a definite integral here. So we're going to get a number out of this. So first we're going to simplify. So this would be the integral between 1 and 9 of 2t squared over t squared plus t squared t to the 1/2 over t squared minus 1 over t squared dt. So now I can do some cancellation here and here, here and here, and I'll end up with the integral between 1 and 9 of 2 plus t to the 1/2 minus t to the negative 2 dt. Right, so now if we go ahead and integrate this, we're going to get 2t, power rule, plus t to the 1/2 plus 2/2 divided by 3/2 minus t to the negative 1 divided by negative 1 evaluated between 1 and 9. So simplifying that a little further, that's 2t plus 2/3 t to the 3/2. Two negatives, that would be positive 1 over t evaluated between 1 and 9. So that would be 2 times 9 plus 2/3, 9 to the 3/2 plus 1/9 minus 2 times 1, using my lower limit of integration, 2/3 times 1 to the 3/2 plus 1 over 1. All right, so this is using FTC2, part 2. So I can go ahead and substitute all those numbers into my calculator and crunch out a number, and I should end up getting 292 divided by 9, which would be an exact answer. So in this example here, we've got two power terms, and then we've got this term here. So if you look back at our table, we'll be using this formula here, where the integral of 1 over x squared plus 1 dx is the inverse tangent of x. That's because the derivative of the inverse tangent of x is 1 over x squared plus 1. So we can write it out as going ahead and taking the integral. We're going to get 2x to the 4th over 4 minus 6x squared over 2 plus 3 times the inverse tangent of x, evaluated between 0 and 2. So this constant here just stays out front. So I didn't have to use the chain rule because this was just a plain x. So that's equal to 1/2 x to the 4th, 3 x squared plus 3 times the inverse tangent of x, evaluated between 0 and 2. So substituting our values in, we've got 1/2 times 2 to the 4th minus 3 times 2 squared plus 3 times the inverse tangent of 2. Now subtracting 1/2, 0 to the 4th, so that's just going to be 0. I'll just write these out. And then 3 times the inverse tangent of 0. All right, some of these terms are going to go to 0. So this is going to go to 0, 0. And the angle whose tangent is 0 is also 0. So this is going to go to 0. So now we're left with 1/2 of 16, that's 8, minus 3 times 4 is 12, plus 3 times the inverse tangent of 2. So you can evaluate the inverse tangent on the calculator. So that ends up being negative 0.678554. So you're going to be in mode radians, so make sure you check your setting on your calculator. So example 3 is an example using the net change theorem. So it says a company's marginal cost function, which is the rate of change of production costs per unit, is C prime of x is 5 over root x, where x would be the number of units. So we're asked to find the total cost C of x of the first 49 units. So this is the net change theorem, where I've substituted in the marginal cost function into my integral. So we want to find the net change in cost in going from A to B. So that would be the right side here. So if we look at a graph of this just to get an idea of what's going on here, we're integrating c prime of x over some x range. So let's say our graph looks like that, and this is your initial value and your ending value. So we're looking for this area here under the curve. Right, and that area under the curve is going to be your cost. And that's because c prime of x would be in terms of dollars per unit. So that's a rate of change function. And then you've got x, which is units. So the units cancel out here, and we end up with dollars. Right, so this area gives you your dollars, and that's what we want. We want our total cost c of x of the first 49 units. So if we want our first 49 units, that means a is 0 and b is 49, from 0 to 49. So I'm going to put my limits of integration on 0 to 49. I'm going to put in my cost function, my marginal cost function, 5 over root x dx. So I can write that as a power 5x to the negative 1/2 dx. So now if I integrate, I'll have 5x to the negative 1/2 plus 2/2, that's 1/2, divided by 1/2, evaluated between 0 and 49. So that's 10x to the 1/2 evaluated between 0 and 49. So that's 10 times the square root of 49 minus 10 times the square root of 0, which is just 10 times 7, which is 70. So my answer tells me that $70 is my total cost of producing the first 49 units. So this example is an example of rectilinear particle motion. So we're given a velocity function, and we're asked to find the displacement and the total distance traveled from t is equal to 0 to t is equal to 8 seconds, where distance is in meters. All right, so what we do know is that the position function is the integral of the velocity function. So the net change theorem tells us that if we integrate the velocity function between a and b, we'll get the change in the position between a and b. And that we call the net displacement. So we need to integrate the velocity function between 0 and 8. So our velocity function is t squared plus t minus 12. And that'll give us our displacement between time 0 and time 8. All right, so if I differentiate that function, I'll get t cubed over 3, just using the power rule, t squared over 2, 12t, evaluated between 0 and 8. So that would be 8 cubed over 3, 8 squared over 2, and 12 times 8. Subbing 0 into any of these terms would just give us 0, so we don't have to subtract anything for this lower limit of integration. So if I find that number, I'm going to find out that that's 106.667 meters. And that's my displacement on the interval 0 to 8. So that answers the first part of the question. Now we need to find the total distance traveled from 0 to 8 seconds. And in order to do this part, we need to know whether the particles switch directions. And the reason we need to know that is because if he did start going in the negative direction, we would have to change the sign on those displacement pieces. Otherwise, we're going to end up subtracting them. So remember, total distance traveled means you're going positive, negative, perhaps. We want to know how far this particle actually went, adding this to this, to this, to this, to this, adding that all up. All right, so we don't want any negative numbers in our addition here. So if the particle does switch directions, we need to change the signs on those pieces of the displacement. So in order to find out whether the particle switched directions, we need to find out the critical values of the velocity. And we know our velocity function is t squared plus t minus 12. So that's a quadratic and it looks factorable. So that would be t 3, 4, positive, negative. So that gives you positive 3 and negative 4. All right, so 3 is the only time in our interval 0 to 8. So we found out that our particle switched directions at 3 seconds. So now we got to find out what direction he's going on either side of 3. So we've got this interval between 0 and 8, and at 3 seconds he switched directions. The question is, which one is the negative interval and which one is the positive interval? All right, so we need to pick an x. So let's say we pick x is equal to 1 and x is equal to 4. All right, and I sub those into my velocity function, and my velocity function is this function here. I'll get 1 plus 1 is 2 minus 12, so it looks like he's going negative in this interval and positive in this interval. And you can verify that by subbing in 4, and you'd get 20 minus 12, which is definitely positive. All right, so that means his position function is negative here and positive here, because change in position, your change in position, if that's negative, if your position is negative, you're going in the negative direction, you've got a negative position, I should say, your velocity is going to have the same sign. So your velocity and your position will both be negative, going in the negative direction. And your velocity and position will both be positive when the particle's moving in the positive direction. So we know that. So what that tells us that we need to do is we need to switch the signs on the displacement on the position function when we're in the interval 0 to 3 in order to make those positive, right? Because we only want to add up positive changes in position, positive movements in order to get the total distance traveled. All right, so here's our position function. And we know that we're going in the negative direction on this interval and the positive direction on this interval. All right, so we need negative t cubed over 3 negative t squared over 2 and positive 12t when I'm going between 0 and 3. And then I need positive t cubed over 3. I'm not changing the signs, in other words, for the interval between 3 and 8. All right, so I changed the signs on the position between 0 and 3. All of these, I reversed the signs, and I didn't change the signs where I know I'm going positive between 3 and 8 on the position. That way, these will be all now positive displacements, positive changes in position, and these will be positive already. So, subbing in my number, All right, the 0 is not going to affect anything. So that's the first piece. Then I've got 8 cubed over 3, 8 squared over 2, 12 times 8. And then I'm going to have to subtract as I'm evaluating this between 3 and 8. So that would be 3 cubed over 3, 3 squared over 2, 12 times 3. All right, so then I just simplify this a little. So I've got negative 27 over 3, negative 9 over 2, that's 36, 8 cubed over 3. We're going to end up putting this in the calculator. So just getting the signs right here. So that's negative 27 over 3. Simplifying this a little before we put it in the calculator, that's 9 over 2, and that's 36. All right, so I typed all that into the calculator, and I got 151.667 meters. And what that's giving me is the total displacement, or the total change in the position, right? The total distance traveled, if you will. All right, my total. So I made all of my negative movements positive, and I added them all together, and between 0 and 8, this particle has moved that far. All right, so that's how you do these kind. So now we're going to do another similar problem, except for this time I'm starting with the acceleration of an object as given by an acceleration equation, which has a sine function in it. We're also given an initial condition so that we can come up with our velocity equation. So part A says find an equation for the velocity of the object. So we just want a function here. We don't want to evaluate it. So we do know that the integral of A of t will give us V of t. All right, so instead of calling them antiderivatives now, we're calling them integrals. All right, and that's what we'll stick with. So if I want to find V of t, I need to integrate 7 sine of t dt and get a function. All right, so I don't have any limits of integration on there. I'm finding a function. So that means I've got 7, let's just say cosine of t, and see if I get the sign right, plus c. So the derivative of the cosine is the negative sine, so I'm going to have to put a negative on there in order to get this right. So the derivative of negative 7 cosine of t would be negative sine of t, which is positive 7 sine of t plus c. Right, my initial condition says that at time 0, so that's time, this is v of t now, let's write that. So if v of t is equal to negative 7 cosine of t plus c, we're told v of 0, so that would be negative 7 cosine of 0 plus c is equal to negative 10. So that's negative 7 times 1 plus c is equal to negative 10, which means c must be negative 10 plus 7. C is negative 3. So part A then, my equation for the velocity will be v of t is negative 7 cosine of t minus 3. So that's part A. Next it says find the object's displacement from t is equal to 0 to t is equal to 3. All right, so in order to find the displacement, we need our net change in the position. All right, so what we do know, because of the net change theorem, is that the integral of the velocity between A and B will give you the change in the position between A and B. So we need to set up the integral between, let's see, what was our time? Between 0 and 3 of v of t negative 7 cosine of t minus 3 dt. So now if we integrate that, we'll get negative 7 sine of t, and that's because the derivative of negative sine of t is negative cosine of t minus 3 times t evaluated between 0 and 3. So now I just substitute in my numbers. So I've got negative 7 sine of 3 minus 3 times 3 minus 7 sine of 0 minus 3 times 0. Right, so we know that this is going to go to 0 and this is going to go to 0. So we end up getting negative 7 sine of 3 minus 9. So if I type that into my calculator, I should get negative 9.98784, and that would be meters. So that's my net displacement between time 0 and time 3. So my net displacement was in the negative direction. Or I should say it's in negative relative to our starting point. So next, we're going to find the total distance traveled. And in order to do that, like we did on the prior example, we need to find out if the particles switch directions at any point within that time interval. So in order to determine that, I need to set v of t equal to 0 and solve for the critical values. So I'm going to set negative 7 cosine of t minus 3 is equal to 0, which is going to give me that negative 7 cosine of t is equal to 3 cosine of t is equal to 3 over negative 7. So the inverse cosine of negative 3/7 in my calculator turns out to be 2.013707, and this would be our time. All right, so that's the time where he switches directions. All right, so now I got to find out which way he was going on either side of that time. So my time interval was between 0 and 3, and that time 2.01 is in the middle there. So if I look at 1 and 2.5 or something like that, and I substitute those into my velocity function, you're going to determine the sign of your velocity function. So when I did that, it was negative on this side of 2.01 and positive on this side. So that means the particle is traveling in the negative direction in this interval, and the particle is traveling in the positive direction in this interval. So we're going to have to switch the signs in order to make our displacement, our change in position, positive between 0 and 2.013707. All right, so we need our position function. So in order to get the position function, we integrated the velocity function. So the position function we got was negative 7 sine of t minus 3t. So that means between 0 and 2.01, we're going to reverse the signs on that and evaluate that between 0 and 2.01 3707. And then we won't reverse the signs between, so these are going to be the same signs between 2.013707 and 3. All right, so now I just have to sub in all my numbers here. So I've got 7 times the sine of 2.013707 plus 3 times this number. And then I've got minus, so I've got this 0 here. 7 sine of 0 is 0. 3 times 0 is 0. So I don't need to include anything with the 0. So now I'm here. So I've got, let's go down a line, minus 7 sine of 3 from my upper limit, minus 3 times 3 for my upper limit here. Now we need to subtract the lower limit substituted in, so minus 7 sine of 2.013707. All right, and then I've got another term, minus 3 times 2.013707. All right, so I've got that whole string of things that I'm going to type into my calculator. All right, so I type that into my calculator, and I get an answer. My total distance traveled turned out to be 14.7435, and that would be meters. So this is my total distance on the interval 0 to 3. All right, and that answers the last part of the question, part C. All right, so that's the end of the examples we're going to do for this section. So you should have enough information to get started on the homework set. Let me know if you run into any problems.